My name is Martin. I'm product manager of Finetech. With an optoelectronics background, I'm really excited to be here in the world of photonics today. And the topic for today is dynamic manufacturing of integrated photonics. We've heard a lot about integrated photonics. But now about who we are. So we are Finetech. Finetech is a Berlin-based company. So we build precision machines, die bonders, precision bonders, which are also being used in the optoelectronics field. And so this is the basic description of our company. It's quite wide. You can use precision and accuracy in many fields, but there's a strong connection to optoelectronic applications since quite a while. So for many years we got in contact with R&D and also manufacturing of these optoelectronic solutions. So you might say, well, I know Finetech. Dynamic, what means dynamic? I really mean speed. So dynamic manufacturing means bring some kind of efficiency in the production of these components. So along the way where we develop and refine our products, I was boiling it down to two questions. And because we are a precision company, it is all about accuracy. So there's always a certain demand of accuracy. But how much accuracy do you actually need in your assemblies? And on the other hand, it's always a trade-off. How much throughput do you need? In the end, it's all a question of cost. Does it make sense to put this into manufacturing? And so Finetech, in the way we build machines, starting from R&D, but also for fully automatic machines, it's all based on passive optical alignment. So structures that we can see, that we can visualize, and to align those as precisely as possible. So alignment accuracy is key. And then to go to the post-bond accuracy. Post-bond accuracy including all kinds of technologies, from thermocompression to UV, curing, epoxies, eutectic bonding, you name it. And on the other hand, there's always the constraint, so there's always a limit. So if you want to go for single mode, efficient coupling, there's a need of active alignment in many, many applications still. But this is also coming with an impact on throughput. So even if you make the active alignment algorithms as fast as possible, there's always the handling that is in the game. So you need to feed components, you have to connect those, and if you can avoid active alignment and you can stick with some passive optical alignment, it has a huge impact, a positive impact on the cost of your product. So focusing on the passive optical alignment for us, it's how to make it faster and not to trade off too much of the accuracy at the same time. When we think about this topic, I was summing up to, there's always bottlenecks, there's always limitations, there's always big questions to answer. And we build machines which uses cameras, pattern recognition, and some kind of movement and motion parts to bring things together, apply force, apply temperature, and keeping everything under control. And we have to deal with the optical and digital resolution. And this means that we need to make things visible. And then we have to calculate positions out of the structures that we see. And coming from the semiconductor field, where you have quite good structures going into the optics, where something is transparent, translucent, it can be a challenge to make things visible. If you have something aligned very well, the next step is to just bond it in place, and there's the mechanical stability. So we need to have mechanical stability throughout the day, having this machine in a production. So it should not run on one day after a certain tweak. So every time you need to understand about the range of accuracy that it provides. And all is combined with the optoelectronics coming with low forces. So in most of the applications we don't need so high bonding forces, so they need to be very low forces to be controlled. And controlling low forces means low electrical noise and having good sensors in place. And on the other hand, the whole tooling that we use to manipulate the parts, to present components, substrates, wafers, the components, they're heavyweights. I would call it heavyweights. It's just not too easy, and it's a lot of metal and heavyweight included in these machines. And all this together, we aim for reproducibility. So everything has to be some kind of reproducible that you can count on it. Because we see before and then we bond. We cannot correct afterwards. So this is passive optical alignment and bonding. Our platform is based on simplicity. So this is also in our slogan, so simply accurate. So we have robustness just by design. Keeping it simple, keeping it neat and slim means that it is better to control. On the other hand, having these machines evolving over the time, we want to tweak it for speed, and we have to find the correct balance of adding weight or adding lightness, I call it, like from the race sports, and in the end it gains speed where we can. And so, and also making this adjustable in the design of the machines. No handling is best. We always have to handle parts, and we have to handle them fast. And without destroying them. They are brittle materials, 3.5, 2.6, so you cannot simply slam tools into components. If you do pick in place and do it in a very gentle way, dealing with optoelectronic components, we need to do it fast and reliable. And also, we need to use quick bonding technologies. So no long time eutectic soldering, but the quick bonding technologies, snap curing, UV, ultrasonics, for example. So just think ahead and out of the box to which technology you can adopt for optoelectronics. So this is a summary of this task that we have to do, and we did a solution for our FINEPLACER, for the FINEPLACER femto, and we refined it in terms of the technological modules that we have in place. We improved it, so some of these ultrasonic and thermosonic approaches, these modules have been improved a lot. At the same time, we try to save cost, and the cost is the total cost of ownership. So these machines have a small footprint, they consume low energy, and so the small overall footprint, I would call it, is quite good for these machines. And in the end, it all stays tailored for your needs. So it's a modular system, it's a flexible system, and so it will be tailored for your specific application. And on the other hand, it is always possible to change it. So this is like a line that I always like to explain how our machines work, and this is the phrase of what you see is what you bought. And this is why we have to focus on the heart of the system, which is the optical system, a stable optical system to make things visible. So the new product that we present these days is the FINEPLACER femto Pro. And it is the essence, it's the latest version of the femto, which is just tweaked to be fast and reliable. And so this is meant to produce things faster for higher productivity and keeping the accuracy under a very good control. We have the same modules that you may know of the Finetech portfolio. It is still very simple. We gain simplicity and we improved usability. So the ergonomics of this machine is improved. It is easier to handle, to program. So from the software part to the usability each day, it has been improved. So coming specific to applications that we can do with this new machine, it is meant for UV epoxy bonding, for example. So it incorporates dispensing technology and UV curing technology, fast curing, ultra fast, like snap curing technology. We can handle the substrates of different sizes and weights. There's like molded optical interfaces or lenses, lens arrays to be placed. And this kind of technology is being used in the optoelectronics, and we think, and also from the experience that we had, that 2-micron bonding accuracy, post-bond accuracy, is certainly enough for most of the applications. So this is where we brought this machine from a sub-micron bonder to a 2-micron bonder, which sounds worse than our top products that we have. But also this machine has a sub-micron alignment accuracy. So with sub-micron alignment accuracy, we can gain these kind of real post-bond accuracy statistically for these applications. Another example would be still the eutectic laser diode soldering. So incorporating a heating plate, higher temperatures, going for gold tin or SAC solder materials, and doing chip on substrate, chip on carrier bondings in various things for single emitters and laser diode bars for high power lasers. And one key is the tooling that we invented for this, to have a really stress-free bonding of laser components, to not only solder it in place accurately in X and Y and Z in space with an overhang or underhang, but also keeping the laser intact, and to have perfect control about the modes, about the polarization of those lasers, especially if you want to combine multiple lasers that you bunch up into high power laser modules. Also for this, 2-micron bonding accuracy is the target. Next one would be a big field of thermosonic or ultrasonic bonding approaches. So we see that the thermosonic and ultrasonic technology has been adopted also by optoelectronics. It's not that easy because this material is really brittle, it's sensitive to handle, but it is possible with a tailored ultrasonic module that you can apply a very good force, low force, high forces up to 100 Newton of force for larger components, and have a perfect power control for the ultrasonic pulse. And this is a very quick process. So in this case, the handling takes longer than the actual bonding. It's just some milliseconds to engage the ultrasonic pulse. But there are other challenges, how the components, how the substrates are being presented and clamped in place, hold in place, to make it possible for the ultrasonic. So we hope that we see more ultrasonic approaches and questions and challenges in future. And I draw down 4-micron real bonding accuracy that would be possible with FINEPLACER and ultrasonics. And now, to sum it all up, we prepared a little video for this machine as a premiere. So thank you for listening, and warm welcome for our new baby in our portfolio. And feel free to visit our booth in the B2 at the Finetech booth. Thank you.